Okay, we want to think about the idea of center of mass. If we have a bunch of masses tending to rotate a massless support about some fulcrum, then the center of mass is the point at which, if we took the same platform and the same fulcrum and added all these masses and placed them at that point. So this isn't to scale, but we add up all these masses and put them at one point so that we have masses distributed at various distances from our fulcrum. And here we have the total of all masses concentrated at one position, one distance from the fulcrum, and doing so we obtain another moment. Then the position here which gives the same moment as the original distribution is the center of mass. Okay, same moment as the original distribution. That's the original distribution that we had up here. Okay, that's going to be our definition of center of mass. Now, in our previous example, the example we just finished in the last clip, we found the total mass of our portion of the sphere in the first octet. And remember, that was a sphere centered at 0, 0, 1, radius 1, basically a sphere sitting on the xy plane with a certain density distribution. We also figured out, let's say, the moments. Now, we didn't actually complete the integrals. I left that to you to do the last few steps, but the moments mxz, where the y position varies, giving us a picture of the y-axis rotated about the 0 point, the origin of that axis, with a bunch of masses distributed over it, very similar to the picture we see here. So we had the moments. First moment was mxz. So now we know the moment mxz, and we know the total mass. The center of mass would be the position on the y-axis where we would basically sum up all of these masses, and this position would be at position y bar. If all the masses are at position y bar, then the total torque or moment is total mass times its position on the y-axis. The total mass would be m times y bar. It follows, if this moment is the same as this, that my bar equals mxz, so that y bar equals mxz over m. Of course, mxz is one integral, m is another integral. We also know the moment mxy. So, very similarly, and I almost wrote that as x. Let's see how am I going to rescue that. Z bar equals mxy over m. And we also know myz, so that x bar equals myz over m. Y bar, z bar, and x bar are the coordinates of the center of mass of that sphere. In general, then, if we can find the moments and the mass, we have, let's list them, x, y, z. X bar equals myz over m. Y bar equals what? mxz over m. Z bar equals mxy over m. Now, what is myz and what is m? myz is a triple integral of y times the density of xyz times our volume increment, which could be dx, dy, dz, dz, dy, dx, whatever. The mass is nothing but the triple integral of the density of xyz with respect to volume. And we can write down the analogous integrals. Okay. I wrote y here, and this should be x because we're doing our x center of mass. Sorry. Our y bar is going to equal the integral of y times density of xyz dv over the integral of the density. And finally our z integral. The mxy, z is the quantity that's varying with our, well, quantity with respect to which the torque is varying. And this is our result. Delta could also be a probability distribution. Now, probability distributions have certain characteristics, but For example, x bar can be interpreted as the mean value of x, and this has a very specific meaning. In terms of a probability. Distribution. Something you might well have seen in a first-year physics class where it applies to a distribution with respect to one variable. We can have probability distributions with respect to more than one variable. And I'll say for now, and we'll be looking at it shortly, that moments have a broader interpretation, higher moments in terms of probabilities and other quantities. For example, as we're going to see in a minute, this is called our first moment. We're integrating x times the density times volume, which means we're essentially integrating x times the mass. If we were to integrate x squared times the mass, we would get another quantity, and you might be familiar with that quantity. We call it moment of inertia. In the terms of a probability distribution, if we integrate x squared times this would be interpreted as the probability of a variable falling within a certain region within our region of definition of the distribution. In any case, if we did x squared, that would give us a different quantity, which we identify with another term that you're possibly familiar with, and that would be the standard deviation. The third moment would be an integral of x cubed, and that also has important meanings, especially in probability theory and also in mechanics and physics.